Have you ever really looked at your salt shaker and wondered what's going on inside? Today, we're going to pull back the curtain on a hidden force of nature, one tiny grain of salt at a time.
I mean, it seems simple, right? It's just salt. Or is it? Turns out, on a microscopic level, there's this incredible dance happening that makes salt, well, salt. So let's find out what that secret is.
All right, so we're going to metaphorically crack open a single grain of table salt. We're doing it to reveal a powerful chemical bond that shapes our world in ways you might not even realize. It's true. Every single one of those tiny grains is a beautiful, perfectly structured crystal. But what's holding it all together so tightly? Let's zoom in and take a closer look. Okay, to really get what's happening, you gotta meet the characters in our little chemical story, the atoms themselves. And trust me, they've got some very distinct personalities. So, on one side, you've got the metals. Think of them as the generous givers of the atomic world. They've got this extra electron they are just dying to get rid of to become stable. And then, on the other side, you've got the nonmetals. They're the eager takers, and they are desperately looking to snag an electron to feel complete. And for our story today, the stars of the show are sodium, a classic metal, and chlorine, a textbook nonmetal. You can probably already see where this is going, a perfect setup for some chemical drama. Okay, so you've got a giver and you've got a taker. The stage is set for a deal, a trade that's going to change everything. So check this out. Sodium is practically begging to get rid of its extra electron, and chlorine is right there ready to snatch it up, and then bam, in a flash, that electron literally jumps from the sodium over to the chlorine. It's not a slow process, it's a clean, decisive transfer. So what happens to sodium after it gives away that negative electron? Well, it's not neutral anymore, is it? It's lost a negative charge, so now it's positive, and it gets a cool new name, a cation. And what about chlorine? It just gained a negative electron, so you guessed it, it now has a negative charge. Its new name, an anion. So now we've got a positive cation and a negative anion hanging out. Okay, so this whole electron trade has left us with two charged particles. And what happens when you put a positive and a negative right next to each other? You probably know this one. Yup, opposites attract. The positive sodium ion and the negative chloride ion are now powerfully, irresistibly drawn to each other. It's like they're tiny little microscopic magnets that just can't be pulled apart. And that incredible force, that powerful pull, it has a name, the ionic bond. It's this super strong electrostatic attraction that locks these ions together, and that is what creates what we call an ionic compound. In this case, our good old friend sodium chloride. And the consequences of this bond are just fascinating. I mean, it's so strong that it forms these really tough, rigid crystals. That's why salt is a solid, right? It takes a ton of energy to break these bonds, which is why they have super high melting points. And, get this, when you dissolve them in water, those charged ions are suddenly free to move around, and they can actually conduct electricity. That's a super important detail we're going to come back to in a minute. Okay, so now that we get the bond, let's learn how to speak the language of chemistry. How do we actually write these compounds down on paper? Here's the golden rule, the most important thing you need to remember. The final compound must have a total charge of 0. Nature loves balance. So the positives have to perfectly, exactly cancel out the negatives. No exceptions. Let's try it out with a different example. Say you have calcium, which likes to form a +2 ion, and chloride, which we know forms a -1 ion. So to balance out that +2 charge from the calcium, how many of those -1 chlorides are you going to need? Right, you need 2 of them. That gives us the chemical formula CaCl2, calcium chloride. See? It's really just simple math. So why should you care about any of this? Well, because once you know what an ionic compound is, you'll start seeing these incredible structures absolutely everywhere. We started in the kitchen with plain old salt, right? But these things are also in the limestone and chalk that make up our sidewalks, cliffs, even caves. And yeah, believe it or not, they're in your favorite sports drink. You know the word electrolytes they're always talking about in sports drink ads? Well, that's literally what they are, just ionic compounds dissolved in water. And those little free-moving ions, your body uses them to carry the electrical signals that make your nerves fire and your muscles contract. How cool is that? Just stop and think about that for a second.
This tiny, totally invisible event, a single electron hopping from one atom to another, is the fundamental process that builds massive geological structures like mountains, and it's the exact same process that powers our own bodies. That's mind-blowing.
So the next time you pick up that salt shaker, just remember the incredible atomic drama happening inside every single one of those tiny crystals. It really makes you wonder, doesn't it? What other invisible forces are out there quietly shaping the world we see every single day?